Hello everyone, welcome to our next very special episode of Conversations about the Cosmos. This is the week of Starmus Festival in Bratislava. My name is Samuel, here is Norby, and we dragged Frank from the main square to discuss universe, to discuss telescopes, to discuss asteroids and other things you can see in the sky. Probably all of our viewers have seen the three-body problem. They know it should be impossible, but we discovered 3 asteroids somehow holding together. How is it possible? Have you disproved the series?
No, I did not disprove the series yet. Sorry. We discovered in 2005, so using the very large telescope in Chile, that an asteroid called 87 Sylvia, which has roughly a diameter of 200 kilometers, has 2 tiny moons, 5 and 7 kilometers, orbiting around that 1,000 kilometers away. Mm-hmm. And they showed that the system is stable for a long period of time, which was something that theorists did not expect. And that was one of the discoveries of the year 2000s for me. Mm-hmm. And what I liked in this research is after discovering them, we could name them as well.
Yeah. What are the names?
So we found out that Poxon, we discovered 87 Sylvia, the 87th asteroid discovered in the long list of millions of them that we have now. We wrote a paper that I read, and he said, well, I named this asteroid 87 Sylvia in reference to, in honor to the Rhea Silvia. And the Rhea Silvia is the mother of Romulus and Remus, the founder of Rome, the 2 brothers. So it was easy to name them Romulus and Remus.
How large is the system?
200 kilometers for the primary, 757.
The separation between them?
Oh, it's 1,000 kilometers, 2,000 kilometers typically.
How do you connect the dots, in this case, literally? Like understanding they are the same system?
Well, you observe them multiple times. So we have, at the time, we have like 7 observations, and you could see the secondaries moving, the moon is moving in almost the equatorial plane of the primary. And these are extremely useful because from the moon orbit we derive the mass and the density of the primary, and we found out that Sylvia is probably the result of a catastrophic disruption of a larger asteroid. So what we are witnessing is the remain of a discussion of an asteroid. And large fragments form the primary, and then there was probably a swarm of small particles and they make those 2 moons.
So I remember from when I was a kid, I used to read the Cosmos magazine, and I remember that when the Galileo spacecraft was traveling to Jupiter, mm-hmm. It visited 2 asteroids.
Yeah.
And next to one of them, it discovered a small moon, and it was a huge surprise. It's a big asteroid called Ida, and there was Dactyl, this small moon. It was back then a huge surprise, and now we know that a large fraction of asteroids have moons. Why is that? How do they form?
There is plenty of different scenarios, and it depends on where they are. So I'm not going to give a lecture about it, but when they're close to us, NEAs typically, 10% of the NEAs near Earth asteroids are binaries, and we think they form by shading material, because asteroids are not inert rocky bodies.
It's not a solid piece of rock.
Yeah, and they also interact with the environment. So when they come close to the sun, due to what we call the Yorp effect, they spin up, and then they take this kind of top shape.
Mm-hmm. And what was the effect?
The Yorp effect is basically the interaction with the solar wind, mm-hmm. which warm.
I'm a theoretical physicist, so speak to me like a child.
So when an asteroid is get the heat from the sun because of its rotation. The heat is ejected from another part of the asteroid, yeah, and this basically accelerate or decelerate the asteroid. It's called the Yorp effect. And if the asteroid is made of thin particles like rubber pile, It will then take the shape of the top shape, as an equilibrium shape, as it spin up. And if it continues to spin up, we will eject material, shade material. So that's giving birth to other asteroids, basically. So those asteroids are infant, those moons are infant of the primary. So we know that this phenomena happen now in near Earth population, and the largest portion of them are binary because of that. In the outer part of the solar system, the trans-Neptunian population, we also have similar, same-size binary systems. And in this case, they form because a long time ago, there was basically a disk of planetesimals around the Sun, and they are more or less the same kind of relative speed. And some of them had close encounter to each other, and these basically capture those systems, and they form these two binary systems. So a significant fraction, we don't have yet a number of trans-Neptunian objects are binary because of this phenomenon. And in the main belt, we have a bit of everything, but the catastrophic disruption seems to be the most likely way to form this binary system or triple asteroid systems. Catastrophic disruption of a large parent asteroids and formation of this large primary and tiny moons in orbit.
So when you were describing this shape from the past spin, these days when spacecraft are visiting asteroids, several asteroids seem to look the same.
Yeah, because of this phenomenon.
And
Bennu has a top shape, Ryugu at top shape, 1999 KW4 at the top shape. I mean, I can name a long list of them.
Yeah.
And this is kind of recent discovery. This happened over the past 10 years, in fact, that we discovered this phenomenon.
So this is one typical shape of asteroids. The other one is the peanut shape, which is also the comet visited by the Rosetta spacecraft. It also has a peanut shape, and asteroid Tutatis and others. So why the peanut shape?
So there is multiple explanations for the peanut shape, but one of them is because they probably were two asteroids that has close relative speed and get attracted to each other, and due to tides, they probably lose their energy and momentum and they collide. So Hermione, 121 Hermione, is a large binary bilobelid asteroid, and you have comets like this as well, etc. So the world of asteroid is interesting to study because it gives us an idea of the past of our solar system. Thanks to simply looking at the shape, the composition, the distribution of material of asteroids, we can have an indication of how was the solar system and how it evolved. We like studying asteroids is like basically doing is basically digging the ground of Earth to find civilization. We're doing exactly the same, but in the solar system.
So you said that these are two bodies that that collide. These asteroids are piles of rubble, right?
Yeah.
Isn't it possible that you have an asteroid that is elongated, it's a pile of rubble, and then it spins up, and as it spins up, it kind of...
Two lobes, yeah, we do have that as well. That's the Darwin evolution of asteroids, and we have great idea and theories, but in fact there is not that many asteroids for which we have a shape, an accurate shape. Mm-hmm. It's very difficult to derive the shape of an asteroid. You have to visit it with a spacecraft, observe it with adaptive optics that we did for Sylvia, or you have to use radar observations but you have to wait for the asteroid to be close to you. We have a technique that we are using now called occultations. I don't know if you want me to talk about that, but it's kind of a...
This is the right place.
Oh yeah, cool. I'm gonna be like super geeky. So occultations is the concept here is that you are going to wait for an asteroid to pass between you and a bright star. So if you are on Earth, imagine that this is Earth and this is the asteroid, where you will see the shadow of the asteroid passing above. Okay? So if you have observers located in a different location, some will miss the occultation, will not see the star disappearing, but those here will see the star disappearing at very specific time. The timing will be change depending on the location on Earth. And this will basically draw the silhouette of the asteroid. So that's a technique we have been using. It's super low cost, but you simply have to move people to the right place at the right time with a telescope. And using these techniques, we're being able to derive the shape of asteroids, and a group at Charles University, Joseph Durek and Joseph Anush, are basically dedicated their work in doing this. They collect together those occultations plus light curve plus radar, and they derive the shape of asteroids. It's a database.
So this is how also the first ring around the trans-Neptunian object was discovered.
Exactly.
Can you tell us about the ring? How does a ring form around them?
We don't know. So this is an asteroid which is special. It's a Centaur, if I remember. Yeah. And of course, I forgot the name of the discoverer. I'm sorry for that. But he's from Brazil, Felipe. I don't know his last name because we always talk to each other and call each other Felipe and Frank, not like doctor or whatever. But Felipe found by occultation the ring, two rings around one of these Centaur. And what they saw is basically the disappearance of the star, and then for a long period of time, and then.
But this ring was discovered by Felipe, but there were observers in Slovakia, Czech Republic, Hungary that provided important...
Exactly. So that's one of the things I like from occultation, and that's what we're doing too with this telescope, is that we can use, basically, it's an international campaign, and there is no borders, and you have people from everywhere in the world that can participate to this kind of campaign. Now, how this ring was formed, it's still debated. One possibility is that the rings is basically the result of some kind of cometary activity from this Centaur, and that form this kind of the structure, and there is some kind of resonance. Not really my field, to be honest. I'm not a theorist. I love to bring them problems. I don't like to solve them. So I'm not gonna say more about that.
Bringing headaches to theorists.
Exactly. That's exactly what I want to do. Yeah.
But you also discovered a very important exoplanet, right?
Yeah, that's.
So we had Michel Mayor last year speaking about not so direct methods. So how can you find new exoplanets by just looking at dots in the sky?
So
to be very lucky.
No, we have
or patient or
one of my colleagues always said when I discover this exoplanet, say, oh yeah, we discovered an exoplanet. He say, well, you did not only discover it, you look for them and you observe thousands of stars before doing it. So let me just phrase a bit like just what's going on here. We know there is exoplanets in our in our galaxy, right? We have, in average, there is 2 exoplanets per star. However, most exoplanets have been discovered by indirect method, as you mentioned. I'm an imager. I like to take images. So the challenge we have in 2005, we gather a bunch of scientists, astronomers, and as engineers, and we say, how are we going to build a system that will be capable of imaging exoplanet, taking an image of an exoplanet. So we created GPI, the Gemini Planet Imager, which is now was in operation in Gemini South and now is moving to Gemini North. South was in Chile and North is in Hawaii. It's an 8-meter class telescope. The optics we have here is our optics which are capable of correcting the aberration of the atmosphere to the nanometer accuracy. We have a coronagraph to hide the main star so we can see the surrounding. So we started the campaign, we observed 695 stars. And in 2005, we detected, in fact, when I say we, it's funny because it was a 2nd grade student who were observing because it was the 24th of December. And none of the big boss were observing, only the grad students. And they saw, by observing 51 Eridani, a star which is a F-type star, so similar to our sun, a tiny dot now, very stable. Into the noise, they saw this dot. And we observe it again and again and again, and this dot ended up being a Jupiter-sized and Jupiter-like exoplanet. So what I meant by that, it's a Jupiter-like because it's far away from its star, typically 5 AU, 5 times the distance Earth's Sun.
Mm-hmm.
It's the same size and mass, roughly 1.7 or 1.2 mass of our Jupiter.
So it's not super heavy.
It's not super heavy, so it's very like truly a Jupiter, and it's extremely young. If I remember, this is 65 million years old.
How do you know?
Because we just ask. Now we have a model, and the model is based on when you form a planet, it's extremely hot,
mm-hmm.
and then the planet cools down. So by looking at the temperature, which is 800 Kelvin for this one, we have theorists for once to use them, and they give us an estimate.
Now we are useful, right?
So this was a major discovery because we designed GPI for that. GPI was one of the most complex instruments ever built for ground-based telescope. It took 10 years, even more, to do the instrument. Bruce McIntosh is a PI. It's a huge group of 100 researchers working together on this project. I'm part of the group, and I'm lucky to basically be part of this team. And then after this, SPHERE, another instrument, competitive at the VLT, discover additional planets, and we have some other planet candidates as well. It's sad because we did not detect hundreds exoplanets as we were expecting to. And that's a bad news for people who search for life like me. Because we know that Jupiter or Saturn-sized exoplanets are extremely important to bring the water from the outer part to the inner part of the solar system, from the planetary system in this case. So we have a wet terrestrial planet. The fact that we don't see that many Jupiter, Saturn exoplanets could infer that in fact the universe is full of extremely dry terrestrial planets.
So it's the very rare Earth hypothesis that we are a very special place. We have Jupiter, we have our moon.
We have a lot of, this could be a 6-hour conversation, but it's true that we have, our solar system is very special in a lot of ways. And the existence of the moon is important for the tides. The existence of Saturn and Jupiter has been extremely useful to destabilize the disk of planetesimals surrounding our sun and bringing the water to Earth. So, but there is a lot of stars.
I forgot to mention your affiliation, and one of them is at the SETI Institute. So you expect SETI to find nothing because we are the only one in maybe our galaxy or in our universe, or what are the estimates?
No, I'm 100% sure we're going to find extraterrestrial life in the next 10 to 15 years.
Okay, 100% or 99 for?
No, 99.99, yeah.
Okay, so by Webb telescope or?
That's a prediction. I think it's going to happen first with exoplanets. Mm-hmm. In fact, we already have a candidate.
Yeah.
K18b, K218b.
So now we are talking about the chemical composition of the atmosphere?
Yeah. So, to go back to the question, life, even if it's very difficult to create life, having a wet environment it's key, we believe, to have complex chemistry. And when you look at our planet, 4 billion years ago, it was not hospitable. There was high radiation, volcanic activity, asteroid impacts. And despite all of this, we have bacteria. So my belief is that as soon as you have liquid water present on Earth and heat energy, we will find life.
So it's easy to create life?
Yeah. Intelligence is another topic. So we will probably find life in the next 10 to 15 years on exoplanets, because there is a lot of them. We get into the point where we are capable of detecting the atmosphere, the composition of the atmosphere. We will probably see life in our own solar system. Enceladus has all the markers suggesting the presence of life. The complex chemistry, see all the molecules that we need, the energy, the water. So I wish we had a billionaire who basically say, okay, let's put 100 million on the table and we're going to build a tiny spacecraft who's going to go and fly through the Enceladus jets, take some sample and do some analysis, very simple analysis such as the chirality or the amino acids or something like this of this type, and we will find life in Enceladus.
So you say that next 10, 15 years, but won't it be always ambiguous, because these are always indirect methods. So something will be found, and and people will be always looking for other explanations.
Yeah, of course.
It will always be questionable. And
remember 1995, or when they discovered 51 peg?
Yeah.
You remember the argument we had? I was a student, master student at the time. You have one paper claiming this is a planet, paper saying it's not a planet. You have like back and forth for like 5 years. It's the way science works. We're not doing science to bring certainties. But
in the end, the evidence was overwhelming.
Because we build more instruments to develop, to do the study.
So when do you expect that we will get such an overwhelming evidence, even though I'm indirect, that most people will agree?
That's a difficult prediction. So I believe that we are going to find strong indication of existence of life in 10, 15 years. And this will be the beginning of a new era. Mm-hmm. It will be easier to approach an institution, to go see some billionaires in the world telling them, hey, we have a candidate exoplanet here with potential life, or we think there is life on Enceladus. Let's build this instrument that's going to improve the sensitivity, detect this type of molecule, and all of this. Science is incremental.
Yeah.
And that's the thing that people need to understand, is that scientists are extremely patient. More patient than most people, I would say. And for me, we find an indication of life, that will be enough for my career. Mm. Then the confirmation that you mentioned and all of the certainties, that will come after with the younger generation. But they will know where to look, and that's very important as a legacy, I would say.
And then the intelligent life? What are your estimates on this?
SETI is about intelligent life.
Intelligent is the eye. So intelligent life. So the search started, I will say, in the 40 years ago. We created SETI Institute. When I say we, I was not part of that. That was Jill Tarter, Frank, Tom Pearson, and other people. Frank Drake joined after. SETI has been focusing on searching for intelligence by looking at radio emission, because in the 80s, 70s, that was basically the technology they were using. We still doing it, but we are not only doing that. I mean, we are doing search for laser pulse, for instance. That's called laser SETI. Those are stations that we drop in different parts of the world. We have now one in Hawaii, one in San Francisco. We're going to have some elsewhere, Canary Islands, Saudi Arabia, a lot of places. We're going to basically look the entire sky, northern sky, 724 hours. Okay, and this will be able to detect pulse of light laser. Imagine that a civilization know we are here because they built already one of those large telescopes. They will want maybe to tell us, hey, we are here, do you want to communicate?
But I see our medieval civilization or ancient civilizations, because they see in the past, so would they be flashing?
We're talking about 100 light years.
And so they are probably clever and they can estimate at this point. They see tribal fires and they know that.
So there is that. There is different search as well, and there is super exotic search. One of them is to use quantum mechanics. So you can look at basically the interferences. If you have a galaxy and a source, you can look at the interferences, basically the rings of the galaxy. It's not my field, but one of our researchers is working on that, and he claims that if there is intelligent life looking at the system, then the interference will stop because of quantum mechanics. So it's basically looking at those rings of interferences at the level of a galaxy to see they disappear. If they do, then there is an intelligence looking at the system. It's very exotic. We have, we are moving in different directions to search for intelligence, but also we're trying to characterize intelligence. We have scientists working on communication between whales and dolphins. I don't know if you have seen that. There's a paper published like 2 months ago, where we have the first communication between a human being and whales. They basically managed to extract the information in the sound of the whales, so they could say hello and have an answer. So that's the first step. And we're doing this because if you want to communicate with aliens or detect a communication from aliens, you need to know what you're looking for. And we have been we have not been looking around at the type of intelligence we have on our own planet. And we're now realizing only that there is intelligence in our own planet, other type of intelligence. So we need to try to understand that.
So Carl Sagan used to say that if we find an extraterrestrial intelligence, it will be a really good news because it means that a civilization is able to pass
the great filter.
The great filter. It will not every civilization will kill itself in a nuclear war or something, but and so if we discover such a civilization, it passes this, so it will be a peaceful civilization which learned how to live in peace with itself and its environment, and from such a civilization we will be able to learn important things. Now there is the book and now the movie, The Three-Body Problem, where there is the dark forest hypothesis that we should hide from extraterrestrial civilizations because they will come and kill us because we mean danger for them. So it's kind of a zero-sum game type of thing. On which side are you?
I'm on the optimistic side.
You are on the optimistic side.
I believe that if an intelligent civilization exists not too far away from us, in those 200 light years, for instance, they know we are here. They already know. Because we are super noisy in radio, we change our atmosphere. If someone study us from far away, they will see the increase of CFC in our atmosphere. They will see the increase of light from the cities over the past 200 years, carbon dioxide and all of this. So they know that we are here.
So if you fell into coma right now, wake up in 50 years, and we will let you know we have made in contact. Would you be surprised, or you would be like, okay?
That would be okay, yeah.
Okay.
I will be super disappointed by the fact that I did not see the contact.
Okay. That's didn't wake you up.
Please wake me up when they do come. But no, I think it's going to happen. Yeah.
Nice. So the other affiliation I forgot to mention is Unistellar, which is a telescope which both of us own.
Yeah.
So
thank you.
Can you describe the telescope? How is it different with ordinary one?
Actually, I would ask differently because I think it's not often that an astronomer creates a product for the use for other people. So I think it's really it's also an interesting story how you, as an astrophysicist, as a scientist, decided to go in the way to create a product for other people who are passionate about astronomy.
So there is multiple answers to this question. So the first one is that as a kid I had a telescope, and as a kid I tried to use my telescope, and it was very complicated. I do remember trying to focus, find Jupiter, find Saturn, etc., and having not a great time, right? And then I went to work in large observatories around the world, where there is this super fancy computer, and you say, go to Eta Carina, and the telescope is moving there. And take the data, and you see the observation accumulating, and you see the image getting better, etc. So I was always wondering, why do we just give this to the people? I as a kind of, we have the technology to do it, we use it in science, why don't we just do that as a product? I thought about it for a long period of time, but then I met my colleague Arnaud Malbach, and he had the same idea. In fact, he already had made the prototype doing this. So my contribution to this project has been essentially to kind of give a meaning to these observations as well. Because we, at the SETI Institute, we're trying to focus on educating the people. We know that if we want people to be interested in science and technology, and to become one day donors at the SETI Institute, because we work a lot with private donors, we basically need to educate the people about what we do, how it works, what the universe is all about, and so on. So when we created this telescope, I thought that it would be amazing if we could also do science with it, citizen science. So we tried to simplify as much as possible the complexity of taking scientific data, what to observe, how to process, how to analyze, etc. And we created the Citizen Science Program of UNISTELLAR. So that's kind of my motivation. But then there is a motivation, a personal motivation. And I'm going to be very honest with you. I mean, I work in the US, I've been working in San Francisco. I'm surrounded by people who have been entrepreneurs all their lives, and some created like 4, 5, 6 companies. Some are billionaires now. I'm not. But it's...
I tried so hard.
For 20 years. But my point is that when you're surrounded by this, in this kind of environment, yeah, you say, let's do it. You probably have a ton of ideas that you never kind of moved forward to, but I decided, let's do it. Let's be part of this kind of movement of creating a company, a new idea. So the world is better too. I mean, this telescope, I love a telescope because you don't kill anybody with a telescope. You enjoy the stars, you educate the people. It's only positive to me. Yeah. That's why we created UNISTELLAR and this telescope and the Citizen Science Program.
So, when I want to explain to someone that physics, astrophysics, cosmology can bring deep emotions, I describe the feelings you have when looking at the night sky. You are studying asteroids, exoplanets, thinking about extraterrestrial life. So, what do you feel and what do you think about when you look at the night sky?
When I look at the night sky, last 2 days ago. I went to, when I was in Prostějov, it was clear, and I went with a friend and wanted to see the aurora. And I was looking at the night sky, and I always have this moment where, when I was a kid, and I was looking at the sky and thinking about whether or not we are alone in this universe. Always been my motivation to find an answer to this question. Everything else I'm doing is basically a way to reach to this, to find an answer to this question. So when I look at this telescope, a galaxy, and I see a spiral galaxy, I always think about the fact that they probably have civilization over there.
Somebody's taking a picture of our galaxy from them.
I think it's extraordinary. So I always see the universe in the mindset of SETI. And I think since when I was 17, I was a hacker, like writing codes and hacking and so on. And I have a text that I wrote in computers, you can find Atari 720 ST, way too young for that. But it was very, the beginning of computers. And I wrote a text that I found because it's now on YouTube. And in this text, I mentioned SETI and the search for life.
So you think about different civilizations. The civilizations may be living, I don't know, on an exoplanet, not too far away. Do you think if you discovered one civilization within 100 light years, it will change how the humanity thinks about itself?
Yeah. The motivation to look for life for me is not to answer to the question whether or not we are alone. Is to give us an optimistic view of our future. If we find someone who went through the same trauma that we went to as a civilization and overcome them somehow, And if we find someone with whom we can discuss and exchange information, we will know that we are not an anomaly into this evolution. Because if you look at the tree of life, humanity is this weird thing where we are biological, intelligent, and technological. And is that truly something stable? Is there a future for species like us? Maybe no. Because, for instance, whales are intelligent, they're not technological, they're biological. And they will be fine in this ocean, on our planet. Maybe humanity needs to transform itself and become this tiny cube of silicium floating in the universe, harvesting the energy of stars. And that means that we will have to get rid of our biological form. So looking for life is a way for us to know if we have a future as a civilization and to find a brother or sister with whom we can exchange information and get some answer, some guidance.
Do you have any more questions, or we'll leave it here at this very positive note?
Frank also discovered the biggest volcanic explosion in our solar system, so I would have a lot to ask him.
I think
as well.
Every of your topics is, I think, worth an episode of its own.
You want me to talk about this? That was my PhD was the use of adaptive optics for the study of solar system bodies. And there was a very interesting solar system body called Io, satellite or Jupiter. I'm from Reunion Island, from my mother's side, and there is a volcano over there. And when I was a kid, I was always fascinated by volcanoes. So of course, the first thing I did when I got access to an adaptive optics system and a 4-meter class telescope is to try to observe Io. Because in the mid-infrared, you will see, it was a thermal infrared, 3 to 5 micron, you should see the heat of the volcano. Right? So we get this weird image with a lot of stuff and kind of a ring and so on. So it was in the beginning of my PhD. You probably remember, you don't know what you're doing, right? So I processed the image, I tried to understand what was that. My boss had no idea as well because it was the first time we observed this. And then I went to a conference in Flagstaff, first time in the US. And Galileo spacecraft have taken a picture of the same hemisphere at the same time. And the two pictures are strikingly identical. So I knew at that time that I had basically seen volcanoes from Earth on Io using a 4-meter class telescope. So my PhD evolved, we measured the brightness, the temperature, blah, blah, blah. And then I go to I finish my PhD, first run, we go to first observation run that I got there. We go to Hawaii using the 10-meter class telescope, the Keck. And we point to our Io. The Keck has a camera which was between 1 and 2.5 micron. So it's extremely boring because Io is kind of homogeneous. We don't see volcanoes at this wavelength. First night, no volcano. Okay, we move to something else. 2 nights later, we observe again the same hemisphere of Io because it's orbiting in 48 hours. And we saw something completely different. It was like a dot, a tiny dot. And then I zoom out and I see Io, and I see this gigantic bright spot on the surface of Io. That was a volcanic eruption that we saw live, basically. It's called CERT 2001, now because it was discovered in 2001. And we measured the intensity and so on, and it covered in 48 hours a surface as large as Los Angeles or London, and the magma at a temperature greater than 1200 Kelvin, which doesn't seem important to you, but at the time we thought that Io has a very low temperature volcanoes, and the amount of temperature magma, and the amount of energy is so great that it's greater than any eruption ever seen on Earth, even the one from the ancient time. So this is the most energetic eruption ever witnessed by humanity in our solar system.
Very cool.
Very cool.
The opposite of cool, I would say.
Yeah, I can talk about this forever.
But I think you gave some inspiration to many people because there are so many different interesting things you can study in the universe, like asteroids, moons, volcanoes. Like volcanoes, why bother with volcanoes on Earth? Those are dangerous. You can study those in the space from safe distance. So I think after listening to this, many people will be like interested. Well, maybe I should go and discover something. But I'm a theoretical physicist, so from my point of view, it's very difficult. So is it really possible for someone young watching us just go point your telescope somewhere and you might discover something new? Or you have to be very specialized and it takes years and years and years. So
there is always things you can discover. And if you want to discover something, you have to observe often. Mm-hmm. That's why I say I discovered the first triple asteroid system, the first volcanic activity on Io, etc. Because I observe Io a lot, I look for it on I observe asteroids a lot. The reason we have this telescope and the citizen science program is to give the opportunity to people to do this kind of discoveries. So we have five citizen astronomers who observed the DART mission in 2002 when the NASA impacted the DART mission on Didymos, the moon of Dimorphos, and they observed it with the telescope. And they saw the explosion live. They saw the birth of material and so on. We put together all the data. I'm skipping the analysis here, but we managed to confirm the amount of energy transferred by the spacecraft to the asteroid. So confirming that kinetic impactor is a method that can be used to deflect an asteroid. And this was done with contribution of people who observe with this telescope. They basically learn as well during the process, because you process the data with them, you explain, and so on. So if you want to do discovery, there is always a possibility. Having a telescope does help. And having a telescope you can use.
Or you can become a part of a collaboration or
you can do project. So there is also these programs which are extremely interesting, where you process by eyes data taken by other telescopes and you try to quantify, classify type of observation.
So actively you have to search for opportunities too.
There is always something you can do.
But you have to have curiosity and perseverance.
Yeah.
That's a fun out of this world.
You do not give up at everything. That's a why.
Yeah. So hopefully one of you, finally we can look directly at the camera, have found this very inspirational, and we'll find something new in the universe. There are plenty of things to find and observe. Right?
Yeah.
And not to forget, I forgot many things, all of your affiliations, but also we have a new book out, so. And it's basically a version of this show turned into a book, so it can last forever, or as long as paper lasts. So, see you next time. Unfortunately, probably not at the house, but we'll have to deal with it later. See you later. Bye.
Bye-bye.
Bye.